Hi everyone. I make this video just in case you have trouble memorizing the expected value and variance of some discrete distribution. I will cover the derivation for Bernoulli distribution, binomial distribution, geometric distribution, and negative binomial distribution. I will not cover Poisson distribution and hypergeometric distribution just because I think the derivation of those two distribution is very, very long and you might not have enough time on your final exam to actually go through the derivation for that. So I will only cover 4 types of distribution in this video. So let's start with Bernoulli distribution. If we let X denote the outcome of a Bernoulli trial, then X has Bernoulli distribution. And we have parameter P. What it means is in a Bernoulli trial, you have exactly 2 outcomes, success and failure. For example, when you toss a coin, there are exactly 2 outcomes, head or tail, and depends on what do you want. You can define head as success and tail as failure, or vice versa. And this parameter P that you're seeing here, it is the probability of success in a Bernoulli trial. So this one here, this parameter P, it is probability of success. And since the experiments only have exactly 2 outcomes, if it is not success, then it has to be failure. Therefore, probability of failure in a Bernoulli trial can be denoted as 1 minus P. And we often call this Q. Okay. So the probability mass function for a Bernoulli distribution is as follows. So as usual, we draw a table of 2 rows. The first row denotes the value that X can take. It can be 0 or 1. We think of 1 as success and 0 as failure. For example, if I toss a coin and I have head or tail, and I define head as the success outcome, then if I toss a coin and I got head, then X will take on value 1. But if I toss a coin and I got tail, then X takes on value 0. It is because I define head as success. If you define tail as success, then it should be vice versa. Like it should be the opposite. And the second row would be probability that the uppercase X denote the random variable and the lowercase x denote the actual value. So in here, I would want to fill in probability that a random variable x takes on value 0. And 0 is to indicate failure, which means probability x is equal to 0 is equal to probability of failure in our experiment. And as given, it is 1 minus p, or you can denote it as q, whichever you like. And here I want to fill in probability x equal to 1, which is probability of success, and it is P. Okay. So this is our probability mass function. You can either write this table, or you can write it as a piecewise function like this. So when x is equal to 0, we have the probability that x equal to 0 is 1 minus p. And when x equal to 1, I have probability that x equal to 1 is p. So we will derive the expected value and the variance of a Bernoulli random variable from this. Let's start with expected value. So by the formula for expected value, I know it is the summation of x multiplied with probability that a random variable is equal to x. And I will take the summation over all the domain. Since x is a Bernoulli random variable, x can only take on two values, 0 and 1. So I first start with x equal to 0. Then this expression, when x equal to 0, will be equivalent to, instead of x, I put in 0. And next, I move on to the case where x equal to 1. When x equal to 1, this expression is equivalent to, wherever I see x, I just sub in 1, like this. And I have 0 multiplied with any number would be 0. So I can disregard this term. And here I'm left with 1 minus probability x equal to 1, which is just probability x equal to 1. And according to our PMF, this is just P. So we just derive expected value for Bernoulli random variable is equal to P. Next, we move on variance. Variance is given by the formula expected value of x squared minus expected value of x and everything squared. So we just derive expected value of x, which is p. So I can know this term is p squared. The only thing I need to find is this term, expected value of x squared. So we will go to find that. Here, I just apply the formula. And the formula I'm applying here is expected value for a function of x is equal to summation of that function multiply with the value in probability mass function. Okay, and I iterate through every x in the domain. So I copy the formula here. Here, the function of x is x squared. So I write down x squared. Again, we are working with Bernoulli random variable. So there are only two possible values for x, which is 0 and 1. So when x is equal to 0, this expression is equivalent to 0 squared and probability mass function at x equal to 0. And when x equal to 1, I have 1 square multiplied with probability mass function at x equal to 1. Here I have 0 multiplied with any number. It's just 0. In here I have 1 square multiplied with probability x equal to 1, which just give me probability x equal to 1. And they just p based on our probability mass function. And remember, we were interested in finding variance of x. We just found expected value of x squared is p. So I put it down. And then expected value of x is also p, but we have to square that. So I have p squared. We see that both term has p, so I can factor p out. And I'm left with 1 minus p. And what is 1 minus p? It is q, which is probability of failure. So we just derive for a Bernoulli random variable. Oops, somehow my pen doesn't work. The variance of a Bernoulli random variable is equal to p multiplied with q, which is probability of success multiplied with probability of failure. Whereas expected value of a Bernoulli random variable is equal to probability of success. Okay. And based on this, we will derive the expected value and variance for a binomial random variable. Let's see. So we have binomial random variable. So let x denote number of success in an independent Bernoulli trial. Then x follow a binomial distribution with 2 parameters n and p. Okay. I have x is number of success in an independent Bernoulli trial. That's what parameter n stands for. It is the number of trials. And probability of success in each trial is p. The probability of success stays the same for every trial. So that's what parameter p stands for. And we cover it in the tutorial that x equal to x1 plus x2 up until xn. And each xi follow a Bernoulli distribution with parameter p. What we are saying is, if you have n Bernoulli random variable and they are independent from each other, then the summation of n independent Bernoulli random variable will give you binomial random variable. Why is that? Because if you think about it, x denotes the number of success in an independent Bernoulli trial. So let's say you have this one is trial 1. And then you have trial 2 up to trial n. And for trial 1, I use x1 to denote the outcome. What does it mean? It means that in trial 1, if I get success, then x1 is equal to 1. If I get failure, then x1 equal to 0. Similarly, for trial 2, I let x2 denote the outcome. If in trial 2, I get success, then x2 is 1. Otherwise, x2 is 0. And we do that for every trial in these n trials. So for trial n, I use xn to denote the outcome. So the total number of success in all those n trials, you actually just look at each trial and count whether they have success or not, right? Which means if you take x1 plus x2 plus up to xn, you will get the total number of success in these n trials. That's why we have the expression x is following binomial distribution with parameter n and p is equal to x1 plus x2 up onto xn. And each of these xi follow a Bernoulli distribution with parameter p. And they has to be independent from each other. And we are interested in finding expected value for x. So instead of x, I will just write down this expression because it is equal to x. And here we apply linearity of expectation. And I have expected value of x1 plus expected value of x2 up onto expected value of xn. And what is expected value of x1? We have x1 is a Bernoulli random variable with parameter p. So expected value of x1 is just p because we just derived it in Bernoulli distribution. Similarly, x2 follows Bernoulli distribution with parameter p. So expected value of x2 is also p. And it is actually true for every random variable xi. So we have a bunch of p adding together. And how many times? We have n random variable. So we have p plus p plus p n times. And this gives us n times p. So we just derive expected value of a binomial distribution is equal to n times p. We can do the same thing to derive the variance for binomial random variable. I will just write down again, x equal to x1 plus x2 up until xn. And we have x1, x2, and xn. They are independent. Therefore, we have variance of x is variance of x1 plus x2 plus up to xn. And here, because they are independent, we can write this as variance of x1 plus variance of x2 up to variance of xn. And what is variance of x1? x1 is a Bernoulli random variable with parameter p. So variance of a Bernoulli random variable with parameter p is P multiplied with Q. Similarly for x2, for x3, x4 up until xn. So we have PQ plus PQ plus PQ how many times? We have n random variable. So we have PQ plus PQ plus PQ n times. So we just derive variance of binomial random variable is equal to NPQ. You might wonder why I didn't start with PMF and then just use the formula for expected value and variance to get this result. The answer is you can do that. It is just a bit more math involved. Now we move on to the derivation for expected value and variance of a geometric random variable. So we first look at what is the meaning of a geometric random variable. The reason why it is important is later we will build on that to get the expected value and variance for negative binomial. So if we denote x as the number of trials until we get the first success, then x follow a geometric distribution with parameter p. And what p indicate here is the probability of success in each trial. So every trial has the same probability of success and they are independent trial. Then we are interested in how many trials do you have to try until you get your first success. So let's first look at the probability mass function. In probability mass function, we're interested in what is the probability that x is equal to k. What does it mean? It's asking you what is the probability that the number of trials until first success is k. In other words, it is asking you what is the probability that the first success appear on the kth trials. So you have a bunch of k trials in total. Then what is the probability that first success appear here? What does it mean by first success appear in this position? It tells you that in the first k-1 positions, it is all failures. In the first k-1 trials, it is all failure. Then what is the probability that this happen? This happen when you have failure, k-1 times, and then you have one success. So it is just probability of failure on first trial and failure on second trial and failure on the k-1 trial, and you have success on the kth trial. And since each trial outcomes are independent from each other, so this can be thought of as probability that f on the first trial multiply with probability of failure on the second trial, multiply with failure on k minus 1 trial, and probability of success on the kth trial. What is probability of failure on the first trial? We know that P is probability of success in each trial, which means 1 minus P is the probability of failure in each trial. So I have 1 minus P together, and then I have the last trial is success, so it is P. And how many 1 minus P do we have? We have failure on first trial, second trial, up until k minus 1 trial. So I have 1 minus P to the power of k minus 1, and then multiply with P. And one condition we have to notice is that k has to be at least 1. And it should make total sense because we cannot have 0 trial, right? Because we want first success. X denotes the number of trials until the first success. So in order to get a success, we need at least 1 trial. And then it can go on up to infinity. So our probability mass function for a geometric random variable is given by this. When k equal to 1, 2, 3, 4 up to infinity. If k is 0 or a negative number, then probability x equal to k is just 0. From here, we will try to derive the expected value. Again, I just write out the formula for expected value. And what is the support of x here? X can range from 1 up to infinity. And what is the probability mass function for x? It is just 1 minus p to the power of x minus 1 and then multiply with p. And what do I do next? In this summation, the term p is not related to x, right? This term is x, so obviously it related to the variable x here. Similarly, for this term, it is to the power of x minus 1, so it has the term x. Only this one, it does not involve the term x, so you can pull it outside the summation.